Hi, welcome to Gases Overview Part 2, where we're going to talk about the kinetic molecular theory of gases and effusion and diffusion. So, the kinetic molecular theory has 5 components to it, okay? And this is mainly describing what's going on in a gas. So, the first one says gases consist of a large number of molecules. That's pretty realistic, right? That are in continuous and random motion. And that's kind of what this picture over here is showing us. They're moving in a random kind of motion. The combined volume of all of these molecules, all of these little molecules, is very small relative to the total volume of the gas. There's a lot more space in between the particles than the actual volume of the particles themselves. Attractive and repulsive forces between the gas molecules can be ignored. They are not attracted to each other or repelled. Okay, so they won't stick together or repel each other. Energy can be transferred between molecules during collision. So if they bump into each other, you could transfer the energy from one to the other. But the average kinetic energy of the molecules does not change as long as the temperature is constant. Temperature is really what affects your average kinetic energy. And finally, the average kinetic energy of the molecule is proportional to the absolute temperature. So temperature is what really would change your kinetic energy. Now, as we read through these, you might be saying to yourself, some of these are not necessarily always true. So this kinetic molecular theory is wonderful for describing what we call ideal gases. And in our next video, we're going to discover that most gases are not ideal. So again, let's talk about some of the parts of the kinetic molecular theory. So one of them said that energy can be transferred between molecules during collisions, but the average kinetic energy of the molecule does not change with time, as long as the temperature remains constant. So let's look at this graph here. Notice we have molecular speed, or you could think of this as velocity. And here we have basically the number of particles at that speed. And you see the blue line is at 0 degrees Celsius and the red line is at 100. So what happens when we raise the temperature? When we raise the temperature, the velocity of our particles increases. You see that there are more particles that are traveling at a large, faster speed than at the lower temperature here. Okay, so your curve will start to get broader and you will have more molecules at the higher speeds as you increase temperature. So the average kinetic energy of the molecules is proportional to the the absolute temperature in Kelvin. Okay? So, if I increase the temperature of a gas from 50 to 100, does the average kinetic energy double? And the answer to this is no, because the temperature has to be in Kelvin. If you wanted to double the average kinetic energy, and you're starting at 50, well, first of all, you have to convert it to Kelvin. So if you wanted to double the speed, you'd have to double this. Okay, is 100 degrees. So if we converted 100 to Kelvin, you see this is not double. So yes, the average kinetic energy will increase if you go from 50 to 100, but it will not double. In order for it to double, you have to double the Kelvin temperature, okay? So how fast do these molecules move? So here's the graph that we saw in the 2 previous slides. And again, they're coloring in the area under the curve here, okay? So you see here at 0, fewer than half of the molecules will move at a speed 500 meters per second or greater. So fewer than half. But at 100 degrees, okay, more than half of the molecules will move at a speed. So here is the area under the curve at 100. So that is more than a half will move at a speed of 500 meters per second. So temperature is related to the average kinetic energy. As temperature increases, the kinetic energy increases. Individual molecules can have different speeds. So actually, before I say kinetic energy, as temperature increases, the velocity increases, and therefore the kinetic energy increases. All right, let's look at this graph here. There's these 3 dotted lines. So this is talking about 3 terms. There's UMP, which is the most probable. So finding a particle at that speed, you'd have the most probability of finding a particle at that speed. Then you have UAV, which is the average speed of the molecules. So because this tail here is tailing to the high end, the average is a little bit higher than your most probable. And then finally you have URMS, or root mean squared speed, and this is the one that is associated with the average kinetic energy. So if you see here, it says the speed of a molecule whose kinetic energy is equal to the average kinetic energy of all the molecules. And that's this line right here. So URMS and molecular mass. In your book, it gives this equation here, where R is the gas constant, T is temperature in Kelvin, and M here is your molecular mass. So at any given temperature, the average kinetic energy of the molecules are the same, and this is important. So if you're at the same temperature, then your kinetic energy is the same. So if you have 2 gases at the same temperature, they will have the same kinetic energy. So if they have the same kinetic energy, then 1/2 the mass times the velocity here squared would be the same for both gases. Okay? And if your gas has a lower mass, so look at this equation. If the mass is lower, that means your velocity has to be higher. So if you have a lower mass gas, the speed will be greater. So if you look at this graph here, we have different gases, and you'll notice that the peak of the curve is spreading to the, like helium's is moving, the peak is faster than oxygen. And if I just write the molar mass of helium here and oxygen, you see as your mass decreases, your speed increases. So lighter particles move faster. So effusion. Effusion is when you have a gas molecule that escapes through a tiny hole. And this is really what happens to balloons. Like if you fill a normal balloon with helium, it will float, but the next day it won't be floating anymore. And that's because the helium escaped out of the tiny holes in the balloon. Okay? So the difference in the rate of the effusion of helium and nitrogen, for example, will explain why a helium balloon will deflate faster. So notice the sizes of your balloons here. The helium one is much smaller than the nitrogen one. Helium has a mass, and nitrogen, so nitrogen is a heavier gas molecule, so it will move slower. And effusion depends on it escaping through this tiny hole here. And in order to escape from this tiny hole, you want it to hit this plate as much as possible, and eventually it will find the hole and come through. So if you are a larger molecule, you're moving slower. You're not going to hit the plate quite as fast, so you're going to effuse slower. Diffusion, on the other hand, would be like if I sprayed perfume in a room, you were sitting in the back of the room, eventually you would smell it because the perfume would have to travel to you. Now, you don't actually smell it as fast as you would think. And that's because So here I spray my perfume and the gas molecules take this random pattern. They keep bumping into other gas molecules on the wall and all that. And then they will finally get to you. If they just traveled straight to you, they would get to you much more rapidly. But that's not the way it happens. Because it keeps bumping into things, it takes a longer time for it to travel. And this kind of jagged little path, each of these are called your mean free path. This is the distance that your molecule will travel until it hits something. Once it hits something, it will change its path and travel until it hits something else. So if you are at a higher pressure, the molecule will travel a shorter distance before it hits something, so it'll have a shorter mean free path. If you are at a lower pressure, everything's spread out further, your particle can travel further before it hits something, so it has a longer mean free path. So Graham's law. Graham's law works on the premise that gases at the same temperature will have the same average kinetic energy. So the kinetic energy of gas 1 will equal the kinetic energy of gas 2 because they are at the same temperature. And remember, your kinetic energy is 1/2 the mass times the velocity squared. So here they're just doing it for gas 1 and for gas 2. So since you have a half on both sides, you could cancel them out. Then if you move all your masses to the left and all your velocities to the right, you end up with this relationship right here. Okay? Now remember, this mass 1 times velocity 1 squared has to equal mass 2 times velocity 2 squared. So think about it. Gases with a smaller molar mass, if this mass is smaller, then the velocity has to be higher. Okay? So now we've set it up like this, and we want to get rid of our square. So you'd have to square root both sides. And basically you get Graham's law, which says the rate of gas 1 divided by the rate of gas 2 is equal to the square root of the molar mass of 2. So notice there's a 1 here and a 2 here. And same thing here. So when you're doing your rates, you want the molar mass that's on the top to be the rate that's on the bottom here. So gases with a smaller molar mass will effuse faster. So helium will effuse faster than, say, oxygen gas. And to just follow up on that, so Graham's law relates the molar mass of two gases to their rate of speed of travel. And a lighter gas will always move faster. And this is the same equation that was shown on the other page, where this fancy M is the molar mass of gas 2 over the molar mass of gas 1. So here they're showing you argon and helium. Helium is much lighter than argon, so the particles are moving faster. So they will effuse out of the balloon, and the helium will stop floating, and notice the balloon shrinks. Okay? So it's important that you realize that first of all, the gases are at the same temperature. So the kinetic energy is the same. But the lighter gas will have a higher velocity. So how can the gases have the same kinetic energy if the lighter one has a higher velocity? Well, again, remember, kinetic energy is 1/2 mass times your velocity squared. So if your mass is light, then your velocity has to be fast. They kind of will cancel each other out so that you get the same kinetic energy. And that is the end of part 2.